All right. Now, bivariate data. This time, I'm going to explain a little bit more on the regression coefficient. Then we'll talk about the lurking and confounding variables, and a little bit more on the difference between y equals mx plus c or x equals to my plus c, because you may need to know both of them in the weights exam. All right? So, objective, recall how to use the coefficient of correlation R to describe the strength of the relationship between two variables. We need to understand that even with a high correlation, there could be other variables with the two variables has a common response. That is the possible presence of a lurking or a confounding variable. I'll explain that a little bit more. Then it is understand that it is possible to predict the value of x based on y. We normally predict the value of y based on x. All right? Now, just remember, when we look at using your class pad, you must recall how to use the Pearson's determine the Pearson's correlation coefficient, or the coefficient of correlation. R² is the measure of how closely the relationship between two variables approximate a linear relationship. And it's generally between -1 to 1. And please remember, quote 3 to 4 decimal places. It's quite important for you to remember that. All right, weights is very particular in terms of coding. Now, what we do is, because we are using y equals to something x, therefore we call this Rxy. I'm going to switch it a little bit later when we predict x based on y. All right? Now, recall what I said last week. If we have R is -1 or R is 1, it's a perfect linear relationship. You can draw a straight line through. Whereas you got a situation like this, where there's not a lot of relationship, that's very little, and really weak or no relationship at all. Those two, anything above 0.75 or less than -0.75, those are considered as strong relationship. All right? So, another way of looking at this is just this table here, strength of bivariate association. If it is 0, it's 0 correlation. So between about 0.25 to 0.75, or actually it's not 0.25, 0.35 to 0.75, all right, or 0.7, it depends on what book you use, that's moderate. Anything above 0.7 or 0.75 is strong to very, very strong. All right, same with here, the other side as well. All right, that will be moderate and strong to very strong. Very strong if we have got a real R of about 0.94, 0.95, we can always use the word very strong to describe. All right, that's possible. All right. Now, of course, you've got the next one. You've got so think about things like, are there any other factors that needs to be considered before you describe the strength of a bivariate relationship? For example, how many data points are there? So if you have 2 data points, for example, something like this, you can never describe the relationship because you can just draw a straight line. Or even something like 4 data points, you can draw a straight line. It's not really worthwhile doing linear regression with 4 points. All right? That is really not much of a relationship. And are there any outliers? Maybe you've got something like this, and suddenly a point which is there, which appears to be wrong, because you may have to draw something up like this, which, strictly speaking, it could just be that way. So you may have issue with outliers. And outliers, I will talk a lot more after the school holiday. So think about what could affect the relationship. Look at the graph. Always go back and have a look at the graph if you have the graph plotted either on your class pad or given to you. Observe where there could be little data or where there could be outliers, which you cannot explain. This table was given to you, so you should know anything above 0.75, strong relationship, and I would say 0.94, 0.95, you can say very strong. That is, I think that would be acceptable. All right, now let's talk about the lurking or confounding variable. So in the example last week, we examined the relationship between the consumption of foodstuff and the number of deaths due to heart disease. Whilst there appears to be a correlation, association, or relationship, it does not prove that foodstuff consumption caused a death due to heart disease. All right? Now, there will be questions which will ask you, can you explain that? And you can you explain why Y is not related to X, or Y is related to X? Is there any other factor that could affect it? You are looking at something like lurking or confounding variables, but what you need to do is you cannot just say something like this. You've got to say a confounding, lurking or confounding variable such as, in the next slide, I'll tell you something like, could be due to more affluent society, consuming certain type of food, or that sort of stuff. Think about a situation, all right? It's not, you cannot just use the word lurking or confounding variable. You've got to think about a situation that other variables might be the explanation, all right? So here, in this case, the affluence of society is therefore a lurking variable or confounding variable that each of our two variables has a common response to. Now, the next one is a little bit morbid in a way, the examples. Think about it is, think about the situation. Can we consider the relationship between ice cream sales and the death due to drowning? I know it's a bit morbid, but this is a really good example because we will not be surprised if there exists a correlation or association, because as the temperature goes up, the sale of ice cream is higher. All right? So therefore, if there are more during hot days, there are more ice cream sold and more people going swimming. Hence, there could be a correlation between ice cream sales and death due to drowning. We cannot assume that higher ice cream sales cause higher death due to drowning. All right? There could be a correlation, but you cannot assume that. That is one thing. So in situation like this, its correlation could be pure coincidence, or the confounding variable, both of them respond to higher temperature. The hotter it is, people go swimming, or the hotter it is, people buy ice cream. All right? The relationship is because of the temperature. So one thing that you have to remember is correlation does not mean causation. That's important. So there are correlation, but one may not cause the other. So when scatter graphs appear to have a correlation, this does not necessarily indicate a cause and effect relationship. Is there a lurking and confounding variable? You've got to think about it. That's where you start thinking, and when you start trying to see whether there's any other reason. Is the apparent association purely coincident? So there will be generally 1 or 2 mark question they will ask. Is there any other variables? You cannot just use the word lurking or confounding. You've got to think about a reason. All right. For example, the ice cream sales and the death because of drowning. Yep.
How would you define lurking and confounding variables?
It's a variable that is, it's a variable that is a common response to two variables. That's the common ground between the two. That link to variables. Okay. All right. Now, when we think about lurking or confounding variable, there are so many examples that I can't really give you everything. In the exam, you never know what is coming up. You've got to think about it. All right, that's that device. It's 1 or 2 marks question. Come up with something. All right, the next thing I want to look at is when we draw the line of best fit. Now, the line of best fit, once you've got your regression line, is also called the regression line. The equation is regression line equation. All right? So regression line equation, what happened is that line actually minimizes the distance between the actual and the predicted. So all the points on the regression line, on the lines of best fit by regression, actually has got what you call residue. Residue is the actual takeaway predicted. Now when we come back from holiday, we will be plotting residual graph. Residual graph is another way for us to see whether a linear relationship does work for the data set. All right. So we'll do that when we come back during the school holiday. At this stage, you need to know residual is just actual takeaway predicted. Now, when the calculator determines a line of best fit for estimating y for given value x, it finds a line that minimizes the sum of the squares of the vertical deviation, which is the vertical distance. All right? So the least square regression line of y on x, which is what I've taught you, is y hat equals to ax plus b. And the coefficient relation is rxy, x related to y. All right? So y is predicted by x. So we could sometimes use ryx as well, which means we're using we're using y to predict x. It could happen. The question, like when I show you the example, using the physics marks to predict maths marks, you can do it the other way, maths to predict physics. From last week, the example I gave you, physics marks to predict maths. So you could use maths to predict physics. So that is, in that case, you could have y hat equals to ax plus b or x hat equals to ax plus b. What happened is you may have slightly different line. But what I want all of you to do is if you could actually get your class pad and enter x and y for this, please. All right? Class pad to do that. If you haven't got one, I've got a spare class pad. Who hasn't got one? Do you have one? Class pad. Class pad. Input the data x and y, please. Input first, we don't have to worry about anything else. It should look something like this. I think this is about the amount of data you'll be expected to input in the test or the exam, I think, but I'm not sure. once you've done that, let's not do anything first. What I want you to think about is whether we could use y equals to mx plus c or x equals to my plus c. All right? So we are going to do the regression twice. One with x least as least 1, the other one with x least as least 2. All right? Once you've done, you can try it first. You can try and see what do you get. What is the, if I use x least as least 1, which means least square regression line of y on x. And then if I change it to x least equals to least 2, which is least square regression line of x on y. Just to make sure that you know the difference with those two. All right. Again, I should have used a couple more decimal places for the constant. You will expect that the two equations to be different. However, the correlation relationship should be the same. The correlation coefficient should be the same. Rxy should be the same as Ryx. So making sure that all of you know how to do the least square regression.
What is the least square?
Least square, all right.
What is
If
that?
we go back, least square means what happens is you want the square of this distance to be the smallest when you add up all of them. The residual square. All right. You will not be expected to know this the definition of that.
Okay,
Right.
just.
But it means that you want when the sum of the residue, the square of this is the smallest amount. So there is a, in terms of class pad, there is a way that it actually works out the closest distance. So did you all get the same answer as I do? Yeah? All right. So what happened is if I plot it both on the same line, you can see that there is a difference in between those two lines, right? And both lines should go through the mean of x and the mean of y. All right, that's important. That's one point that you should know. Both lines, it doesn't matter whether it's y on x or x on y, they should go through the mean. The mean of x and the mean of y. So far, I haven't really seen a question which asks you to find the mean of x and mean of y, but you should know how to do it, right? Because with your calculator, you should be able to find. I haven't seen any question like that, but that is something that you need to know. So you could have y equals to something or x equals to something. I have only seen one question which asks you to find the least square equation y equals to x plus something, and then find the least square equation of x based on something. It's just basically changing the x least and y least, that's all. I've seen it once. I think that was one of the exam questions. All right, so what I've done today is really making sure all of you understand R, the correlation coefficient. Now, in the exam or in the test or in anything, when you're asked to talk about your observation, you must always mention the R, all right, whether the correlation is strong or not, all right. If you ask to comment on the data, the set of data, this is one of the things that you have to mention, all right. Tomorrow we'll talk about the correlation coefficient. You will have to mention that as well, all right. And then we come to the residual plot, you have to mention what the residual plot is. So what I would do is by the end of the first week, we should finish the whole of this linear regression, and I've got a couple of lessons to go through all the finer details with you. Alright, I'm going to stop here today. And hopefully I've shown you a little bit more about the coefficient of correlation. And you should understand, even with a high correlation, there could be variables which has a common response. The common response is the lurking or confounding variable. Alright? And finally, it is possible to predict the value of x based on y.